Jnanam Paramam Dheyam. Knowledge is supreme.
Addition of angular momentum. It is not a scalar addition. That's the first important thing. So, addition of angular momentum is a very important topic which you have to use in most of your atomic, molecular and nuclear particle. So, you have to be attentive to know what is addition of angular momentum. Okay, so that's the theme. So, spin-off particle we have extensively studied by looking at the Stern-Gerlach data, that it has two states. The linear vector space is two-dimensional, right? But technically, once I say it's a spin-half particle, you need to remember that the particle is in the physical space and then it also has an internal spin space. So, physical space you can either put a position basis or you could also use the angular momentum basis, orbital angular momentum basis. Okay. So, this is what we call it as a direct product space. The direct product space or tensor product space is a product of the physical space multiplied by its internal space for the spin half particle. Okay. The internal space ms will be upspin or the downspin is the notation. Okay. So, let me write it for you. So, when we write a state, I can write this as a direct product state. Equivalently, you also write m I am not putting an S because I am taking S to be half. That is the only reason. These are equivalent direct product space. When I want to do LZ will operate on LML and it will be like an identity operator on MS. Suppose I do SZ will operate on MS and it will be an identity operator on LML. Clear? So, even though I write SZ operator, it will go and operate on the respective state in the direct product space. So, this is what is the meaning of LZ operator in the direct product space. Even though I will write LZ operator on this, you need to know that this LZ operator on this means this one. So, this is what is the direct product space where you have orbital angular momentum space separately and spin angular momentum space separately, and we work with this. So, if you have an LZ SZ, so you have to operate LZ on this state and SZ on that state. It can change the order. Why is the reason why you can change the order? Tell me. They come in two different spaces. Say LZ SZ is 0. They are in two different spaces. So, the same holds for L squared also. Same holds for L squared. L squared will operate on LML and identity on MS state, and similarly S squared will operate on MS state and identity on the LML. I am just keeping this order in the sense that the first ket represents the orbital space or the physical space and the second ket represents the internal space. This is just a nomenclature. So, what is this? L squared on LML, all of you know. Similarly, LZ also you all know. So, I do not need to repeat it, right. So, L squared will be L into L plus 1 H cross squared, LZ will be So the direct product space spanned by position ket or LML and two-dimensional spin space given by MS. What happens to the rotation operator? Rotation operator formally for any spin j, how did we write? We had an exponential of, this we had extensively discussed in the earlier lectures, it's j dot n, but j is composed of sum of two orbital angular momentum and spin angular momentum. That sum has to be seen in the direct product state as LZ will operate on the LML, SZ will operate on the MS. You have to remember that. So in the same way, can we write this UR operator in a neat fashion? So UR n hat theta is exponential of I j dot n by h cross times theta. I could write this in the direct product space as e to the I L dot n by h cross theta, direct product e to the I s dot n by h cross theta. Is that correct? So this operator will operate on LML. This operator will operate on, so if I want to write what is UR n hat theta on LML cross MS, that will be e to the I L dot n hat by h cross theta on LML crossed with e to the I s dot n by h cross theta on MS. Is this clear? So it separates, it operates on this. The L operator should be treated like an identity operator on the MS state, and S operator should be treated like an identity operator on the. So J is formally a sum. People will write it as a sum of orbital and spin angular momentum, but you should remember that it is on the direct product space. So this is what I was trying to say. Formally when I write J, the J operator on a direct product space should be treated as L operator on the LML state, an identity on the MS state, and similarly identity for the LML state times the spin operator on the MS. Many textbooks don't write this. Many textbooks write J is L plus S. But when you are operating on the direct product space, you have to make sure that it has to be done this way on the direct product space. This is at the back of your mind when you are doing it. They don't write this identity anywhere. Many books don't write. They write L plus S. But technically you should know that on the direct product space, it is identity for the internal space for the orbital angular momentum operator and identity for the spin operator in the position space. There are some things which I want you to check yourself. You can take the square of this, operate it on this arbitrary state. A simple exercise to show that J squared. So J squared is L squared cross identity plus identity cross S squared. You can write it that in the direct product space. And if you try to operate, you can show that J squared commutes with L squared. This is an exercise for you to try it. Similarly, J squared with S squared is also 0. So you can also write Jz as Lz cross identity plus identity cross Sz. And also check Jz will commute with J squared. What does this set tell me? If I have this set which is written in terms of total angular momentum, total Jz and S squared and L squared, is this a compatible set? Is this a compatible set? This is a compatible set again, okay. So you can have two compatible set. J squared with L dot S. No, that is fine, but I am just trying to say that the L dot S here, equivalently you can check this out for you. J is L cross plus identity cross S. So J dot J, when I do, you are trying to say that there will be an L dot L cross identity plus identity cross S dot S, but then there will also be cross terms. That is a good point. Yes, you will have the cross terms. From here multiplied with this, which will give you an L cross S, and then you will also have twice, right? Just twice of this. Yeah. Good point. Yeah. Sorry, I made a mistake in earlier. So you will have this term, and this is, in some sense, it's like the L dot. You have to remember that there should be a dot here. It is, it's, even though I write it as the side is a scalar, so you have to take care that it is a scalar. So this will hinge on this information. This also I want you to check what it is. Okay. So I am just trying to tell that J squared, this is for you to check, L squared equal to 0, J squared with S squared is 0, and you can also show J squared with JZ is, this is trivial, this you all know. So this gives you one compatible set. Can I denote that compatible set neatly? I can denote it. I don't need a magnetic quantum number of L and S, but I need a magnetic quantum number of the total J. Okay. So I will write Jm. Jm is the total magnetic quantum number, and then you can have an L and S. You can denote something like this. So this is a simultaneous eigenstate of L squared, S squared, J squared and Jz. Okay, this is a shorthand notation of writing a simultaneous eigenstate which for this compatible set. So we have written a total magnetic quantum number here. We have not written separately, that is not there in this set. What is the other set possible where we can get the magnetic quantum numbers? We also know L squared LZ is 0. We know S squared SZ is 0. We also know L squared with S squared is 0. L squared with SZ is 0. Is this also a compatible set? What is this compatible set? I can write L, S, ML, MS. What is the difference between these two sets? This keeps the tag of orbital quantum number and the spin quantum number, the magnetic quantum numbers. The magnetic quantum numbers of the orbital part and the spin part, it keeps tagged. So it is like, I will say this piece is the orbital quantum number, this piece is the spin quantum number, then I have this information together, right? I can equivalently write it as L, ML cross S, MS. This is a direct product space. So this direct product space is sometimes said that it is a uncoupled basis. Why? I can say which one is the orbital quantum number and which one is the spin quantum number. So this is what we will call it as a uncoupled basis. This is also one set. So this is one set, compatible set, and the basis is called uncoupled basis. The reason is that it keeps tag of separately orbital and its magnetic quantum number and spin and its magnetic quantum number. The other basis which I wrote is also another equivalent compatible set, but then that one keeps track of the total J and the total magnetic quantum number, which is like a combined, it is combined. You don't know which component is orbital in it, which component is spin in it. You cannot make out. Okay. So, in some sense, we call this to be another equivalent basis, which is called coupled basis. Okay. It's called coupled basis. You cannot have an individual identity of what is the magnetic quantum number corresponding to Ml and what is the magnetic quantum number corresponding to Ms. Suppose I say M is some value, it can be made of all possible things. So, that is why it is called as a coupled basis, and the other one is called as a uncoupled basis. As long as you are in a system, especially in your experimental system, if there is no interaction, like as he already pointed it out, if you don't have an L dot S term, okay, if you don't have, suppose I have, if you turn on a magnetic field, you have the magnetic moment which is dependent on Lz times the magnetic field, and spin magnetic moment which depends on the spin quantum number. Suppose you have an L dot Z term, L dot S term. So, this is what experimentally could happen. This is called spin orbit interaction. Okay. So, typically your Hamiltonian to start with, let me call the initial Hamiltonian to be a mu dot B, which could be having orbital piece plus spin piece. Let us take the B along the Z direction, take B to be mod B Z cap. You could have that H naught to be proportional to Lz plus Sz times B. Here Lz is separate, B is S is separate. But I could turn on something, an interaction, which is L dot S. So, if I do this interaction kind of allows us to go to the coupled basis, okay, because you can try to write what is the total angular momentum and start working with it. You could do this in uncoupled basis, you could do this in coupled basis, both are equivalent. What do I mean by equivalent? If you remember, when we did this two-dimensional vector space, we had one basis, we had another equivalent basis, then those two bases are related by, say, unitary transformation by which you can relate one to the other. Okay. Similarly, for such a system, you could work with uncoupled basis or coupled basis. Sometimes coupled basis will be convenient, and then you should also know how to go from one basis to another, and that matrix is the famous matrix. So, you have a LS JM, you also have LS ML MS, and you have a unitary matrix which relates them. Okay. Both are equivalent. What do I mean by equivalent? The dimension of this vector space should be same as the dimension of this vector space. That we have not yet checked. But once I say it's equivalent, that's what you did. When you did a rotation of the basis in a two-dimensional vector space, you can't get a three-dimensional vector space. It's still two-dimensional. Unitary transformation doesn't take the dimensionality of the vector space. What is the dimensionality of this vector space? 2s plus 1, 2l plus 1. So, that is the dimensionality of that vector space, which is an uncoupled vector space. So here I have not specified what is J. I have not specified what is J. But definitely M will go from minus J to plus J. That's the definition of the angular momentum algebra for every J. But there are so many values of J here. What is the dimensionality for a specific J? It's 2J plus 1. And then you have to sum up over some J which is J min to J max. I didn't say what is the values J takes. Let's assume it takes from J min to J max. Let me not say what that value is. What is the requirement? If they are equivalent bases, this sum should add up to the dimensionality of the vector space has to be matched, and J has to be either integers or half odd integers. It goes always in steps of 1. Okay. So these are the restrictions which we have, and there is a matrix which relates the same dimensionality basis to the same dimensionality equivalent basis related by this matrix. How can we write this matrix? We also know how to do this. Let's do that. We can insert. So if I take this, if I take this, I can insert what is this insertion? It's a complete set of bases, complete set of uncoupled bases, right? And I'm putting the same state which I had on the left hand side. So what is this matrix element now? So this is this. It is that correct? Matrix element is a matrix which connects coupled bases to an uncoupled basis. That matrix element is nothing but the inner product of these states. I'm doing whatever we knew from quantum mechanics tools. I'm not really, I'm trying to push in this concept, but I'm slowly trying to get you to understand that there are two equal and compatible set. One you can call it as a coupled set, other one is called as an uncoupled set. You can work with both of them depending on convenience. I said spin orbit coupling when you have, it's much easier to work with coupled bases. You could work with uncoupled bases also. It's nicer to work with coupled bases, and you should know how to go from one basis to the other, and the matrix elements are given by just taking the inner product. Is the concept clear? So two equivalent bases for the direct product space. One is what I called it as a coupled basis. Other one is the direct product basis, which is also called as an uncoupled basis. Most of the books, once they start saying I'm going to look at a specific particle with orbital angular momentum as something, L equal to 1 and S equal to half, they may suppress this L and S on both coupled and uncoupled basis. Many times they don't really worry about putting this orbital specifically and S specifically. They are more worried about putting the magnetic quantum numbers for them in the uncoupled and the total magnetic quantum number for the coupled. Okay. So this is something which some books might not write all the four, but it is incorporated. It is there.